We're going to talk about the moment generating function. So the expected value of random variable raised to the nth power is called the nth moment. So we've seen the expected value of x, that's sort of the weighted average of x. We've also seen the expected value or weighted average of x squared when we calculated var, because the var x is equal to the expected value of x squared minus the expected value squared. And just to remind you, when you look for an expected value of a function, it's basically the weighted average of all the different values the probability can have times the function density. Again, it's a weighted average of all these values, and the weights are the probabilities. Okay, so you can calculate these nth moments, but sometimes this integral can be ugly. So we use something called a moment generating function, which is defined here. So our moment generating function for a random variable x is the expected value of e to the tx. So we can calculate that using this formula, again using the integral, which sometimes is easier to do than this one. But also once we have this, then to generate the nth moment, all we have to do is take the nth derivative and then evaluate it at t equals 0. So this allows you, especially easy if someone gives you the moment generating function, it allows you to calculate the nth moment using only derivatives, which are generally easier than integrals. So an example, if we look at the exponential distribution with beta equals 1, our density looks like e to the minus x. Again, beta is equal to 1. So to find the moment generating function, we take the expected value of e to the tx. That's just the definition. So we integrate e to the tx times f of x. In this case, f of x is equal to e to the minus x. So simplifying the exponent, we have this integral here. And also, instead of going from negative infinity to infinity, for the exponential, we're going to go from 0 to infinity. In this problem, we're talking about a time, so it's going to be 0 to infinity. Sorry, I didn't give you the whole problem written out. So when we do the derivative, we're going to get 1 over t minus 1 e to the t minus 1 to the x, evaluated at 0 and infinity. And again, with the problem, this is a problem when you plug in the infinity, but if you assume that t is less than 1, and this comes from the problem, you can get 1 over 1 minus t will be your moment generating function. So again, you can calculate the moment generating function, but often the moment generating function is given to you, and then you're asked to find the nth moment. So to find e to the x, the first moment, or the expected value of the function, you take the first derivative of the moment function and then set t equal to 0. So the first derivative of 1 minus t to the negative 1 dt is just 1 minus t to the negative 2, evaluated at 0 is equal to 1. Then if you wanted to calculate the second moment, you're going to take the second derivative of this moment function, which is just the derivative of 1 minus t to the negative 2, evaluated at 0, gives you 2. And then if you wanted to calculate var x, it would just be the expected value of x squared, which is 2, minus the expected value squared. Second example, geometric. So we know from past chapters that the expected value of the geometric function is 1 over p. That's the probability of success. Q is the probability of failure, and we have this moment generating function that someone else has calculated for us, which is very common, and then you'll be asked to calculate the first moment. So then you take the derivative of your function. You're going to have to use the quotient rule. So here it is, the quotient rule, the top times the derivative of what's on bottom minus what's on bottom times the derivative of what's on top, all over the bottom squared. And you can simplify this, but why bother? Because if you set this t equal to 0, all these e to the t's become 1. A little more simplification, and then also noting that 1 minus q, and then 1 minus q is just equal to p. I have p over p squared, and then I get 1 over p, which is what we have seen before in previous work.